All right, so up to this point, we have a decent idea of how to make single bonds by directly overlapping orbitals to form those sigma bonds or sigma orbitals where the electrons are shared. But how do multiple bonds work in this model? We know that every individual orbital can only hold 2 electrons. That's from the Pauli exclusion principle. And so we can't fit 4 electrons into a sigma orbital, but we need 4 electrons if we're going to share those to make a double bond between atoms. So how exactly do we do this? And we can answer this by looking at this molecule, CH2, where there's a double bond between the 2 carbon atoms. And looking at this, we can note that there's only 3 electron domains. There's the double bond, and then there's the 2 carbon-hydrogen single bonds. So we don't need 4 identical orbitals to form 4 identical bonds. What we really need is something a little bit different. So in this case, if we look back at the just normal atomic orbitals for carbon, we have the 2s and then the 3 2p orbitals. Rather than taking all 4 of those orbitals and hybridizing them to form sp3 hybridized orbitals, we take only 2 of the p orbitals with the s orbital and make 3 sp2 hybridized orbitals, but we leave 1 of the p orbitals free. If we look at this arranged around the atom with the large lobes showing of the hybridized orbitals, we can see that the hybridized orbitals are in the plane, and then the p orbital that's left over, which remember has 2 lobes of equal size, that sits above and below the plane. Now, how do I use this to make multiple bonds? Well, let's just take the case where we have 2 of these carbons, and we hybridize them both in this form. If we bring them together to first form single bonds, we'll see that we can easily form a single bond or a sigma bond between the carbon and hydrogen by direct overlap of those orbitals. And we can form a carbon-carbon single bond by direct overlap of the sp2 hybridized orbitals. However, what that leaves is 1 p orbital on each carbon that sits above and below the plane. And those 2 p orbitals, when we bring those carbon atoms together, they actually overlap in a sideways manifold to form a bonding region above and a bonding region below the plane. And it's this bonding region that's illustrated here, and there's 2 of them, but it's considered just 1 bond. It's this new region of space where the 2 electrons can exist that is referred to as a pi bond, and this forms the second bond of the double bond between the 2 carbons. We can look at this in a slightly different representation just to hopefully help visualize this. So if we start out with the 2 sp2 hybridized carbons, it's got its 3 sp2 hybridized orbitals in purple, and then it has a pink p orbital that's just left over that sits above and below the plane, each of them. If we bring in the hydrogens, we can do direct overlap to form sigma bonds, and we can directly overlap the 2 carbons to form a sigma bond there. But then finally, as we bring those together, the p orbitals overlap in a sideways fashion. We form this new bonding region above and below the plane, where the 2 electrons for the double bond sit. Now, there's maybe 2 lobes to this, but it is just 1 bond. So let's do an example of this. If we take CH2O, the Lewis structure tells me I have a double bond between carbon and oxygen, and the VSEPR model tells me this should be trigonal planar around the carbon. And if I look at this and take the carbon, and rather than doing sp3 hybridization, if I do only sp2 hybridization, I can get a new structure that will look something like this, where both the carbon and the oxygen have done sp2 hybridization, so they have 3 sp2 hybridized orbitals and 1 free p orbital. The sp2 hybridized orbitals, which are in purple, form the single bonds by direct overlap, and thus those are sigma bonds. But then the 2 p orbitals, the one on carbon and the one on oxygen that are left, form this sideways overlap, which is known as a pi bond, and that is thus the second bond of the double bond. So to summarize, sp3 hybridization occurs for any atom that has only 3 electron domains around it rather than 4.